Okay, good evening, everyone. Welcome to another new week and to another new session on machine learning. So, we've done a lot already over the last couple of weeks, basically running through all the foundations and fundamentals of machine learning, starting from basic stuff like linear regression, logistic regression, and then moving on to a bit more things talking about classical machine learning algorithms, decision trees, random forests, right? And then we went into clustering, right? Now, in all of this, one of the things that we've found is, or what we've seen is that no matter what algorithm that you use, right? And we're going to talk about more algorithms in the future, right? In the coming weeks. We'll talk about neural networks basically and deep learning. And these are all just different ways of representing models. A model is just a way of representing um, information or approximating complex functions that you can use to predict events, things that happen, right? That's what a model is. And there are different ways you can set these models up, different approaches, different algorithms, basically, right? But in all of this, we find that the most important thing is not just the model itself, it's actually the data. If the data doesn't have any information in it, you cannot extract. In other words, you can't squeeze water from a rock, right? So no matter how well designed or how innovative a model that you come up with, if the data doesn't hold information, your model cannot learn from it. Your model is basically extracting the relationships, the inter interactions, the correlations that exist, right, in your data. That's what the model is doing. And then it is able to predict it. So you don't need data, lots of data points again, right? Or more importantly, if you have a new set of data points or a new set of independent variables, you can use your model to predict what will happen or what the dependent variable will be. But at the end of the day, the data has to make sense. Bad data will give you bad models. So what do? You have to clean data, right? You have to figure out how to pull out those relationships in data. And that's where we come to feature engineering. And we talked through this last week already, so I'm not going to dwell much on it, right? The main objective in feature engineering is to be able to extract, the useful information or to not extract, to remove the noise as much as possible from data before you send it into your model for training. Or more importantly, apart from removing the noise, but also see how you can extract a bit more useful information from the data before you send it to your model so that your model learns better and faster. That's really what it is. So when we say drop missing values, right? That's noise. When we say fill missing values, you are kind of enhancing the data, right? And there's so many other things. When you say create additional orders of the same features, maybe combining them in different ways, you are enhancing the data. So feature engineering is all about cleaning the data, removing noise, right? Removing what does not contain information from your data, and then enhancing what contains information, adding, more information into it. So that's really what it is. You transform your raw data into features, which you can use for your machine learning models. This is what I said. Models fail when data is bad, not when algorithms are bad. So you could even say there's nothing like a bad algorithm, right? Well, you could just choose the wrong algorithm, but there's nothing really like, oh, this was a bad algorithm. Okay. So 80% of machine learning success comes from having good features. Okay. So, the aspects of feature engineering selection, which features should you choose, creation, we can generate new features, transformation, transform those features into ways that will work. So we talked about different kinds of transformation, encoding and scaling being the two main types. Encoding is for non-numerical data like text or categorical labels and so on. You have to turn them into numeric representations. Scaling is what you do on numerical features already, right? But you try to put them into a range that will kind of make the features match in terms of their influence on the outcome. So um, what's a feature? We talked about different types of features. You have numeric features, you have categorical features, you have datetime features, you have text features, you have derived features. So I already went through all of this, right? And then additional ones will, data cleaning. We went into data cleaning. We talked about what is data cleaning, why do we have data cleaning, right? And you know, what happens in data cleaning. We said data cleaning is the first step. Like I said, you want to make your features make sense. You want to remove noise, okay? You want consistency. So your data must be consistent, complete, accurate, and it must be free from duplicates or obvious errors. So some of the things you can do is handle missing values, remove rows that are missing, fill with mean median mode, use simple models, use domain rules. So we are going to look at some of these examples of things we can do. Fix inconsistencies, incorrect types, bad formatting, inconsistent labels, remove duplicates, handle outliers with winsorization, capping, or log transform. Then after that, you transform the features. So what are the things you can do? Normalize the ranges, reduce the skew, improve numerical stability, make patterns more linear, prepare data for algorithms that assume a normal distribution. So the first thing you could do is scaling, which is standardization and normalization. Standardization is when you center around mean of zero and standard deviation of one, right? So these are good for linear models, logistic regression, for neural networks, and for SVM, support vector machines. Then we have normalization, right? So for normalization, it's basically min max, right? So you scale values to a range of 0 to 1. So the lowest value will be 0 and the highest value will be 1. Then you also have log square root box Cox transformations, which are just changing the relationship between the numbers. We have binning and bucketing, which reduces continuous values into categories. So values like ages, age groups, salary bands, risk levels, these are things that you do them, these are numeric, right? But what you want is not numeric. You don't want them to be numeric, right? So you convert them to categorical. So that's basically what that does. So these are some of the things that you will do in order to make your data cleaner. And then when you are done with that, then the next thing would be um, the for non-numerical values, right? Categories, for example, you would do um, categorical transformation. So one-hot encoding. So one-hot encoding is where you are basically using a vector. And then for each class in a category, you basically just generate what we call a one hot vector for each class. And that one hot means it's a positional kind of encoding, basically. The position of that class in its list of categories, that single position, you give it a high value, like a 1, while the rest of the positions, you give it a 0. So we are going to look at some of these um, and how can you seek it to do it, scikit-learn, sklearn. Then we have label encoding where you just translate the, you assign labels, assign numbers to labels, but it may it's only really good where there is an ordinal relationship between categories. So an ordinal relationship is categories where one is there's a kind of order of which one is greater than and so on, right? A nominal relationship is there is no such order. So you need to be careful. You cannot, if you use level encoding for nominal categories, it may be problematic. Normally, you would use one-hot encoding for nominal categories. Then we have frequency, which count encoding, count how many times each class of a category has occurred, and that would be its encoding. Then we have target encoding, where you can replace the category with the mean of the target. In other words, the mean of all the values in that category. Yeah, then we have mathematical transformations, which just basically using mathematical formulas, division, multiplication, and subtraction. So you get ratios, you get multiplications, and you get differences. Polynomial features is where you add additional polynomial features. In other words, some of the features you square them or cube them or something, increase the degree so that if for some reason that feature actually has a polynomial relationship, that becomes easier for your model to learn. Interaction features where you combine different features that may or may not have some kind of interactivity. Aggregation features are features where you aggregate, um, you know, all the values in a feature and you create sums or means or, counts and so on. They have rolling window features based on time series, where you are taking mean over a particular rolling window of time. They have binning, where you take you take the continuous numbers and you chunk them up. Well, not really chunk them up, but you bin them, right? You group them into categories based on the range. Then feature creation, extracting time-based patterns from raw timestamps. So this time is now creation of features based on date time. So um, one is you can convert um, a string into actual date value, right? A string into actual date value. So this is a good example. To date time is a pandas function I used to do that. Pandas has a lot of nice functions that you can use for doing feature engineering and cleaning on dates in particular. Um, and why dates, you need to handle dates very correctly is because dates basically determine a lot of things, right? Date follows chronology. It follows, the movement of time. And the movement of time determines things to an extent that there's always a correlation. So it's always good to be able to convert time properly. If not, your models may not be able to properly interpret, or the time features may not be properly translated, into the models to learn from. So some of the key components that you can extract from date fields would be, for example, the year, right? So you use these functions here. You can extract the year, you can extract the month, the day, right, of the month, the hour, right, the day of the week, whether it is a weekend or not. Those are additional features that you can extract and create from a date field. Then the other thing is we talked about time since an event, which is lag feature, right? Where you can just say, okay, this is the time. Basically, it's a difference, right? As opposed to the actual time itself, which is the time range or the timestamp, right? Then rolling aggregate, we talked about that already. You can do a rolling window, but if you do a rolling window on a date field, then you have an interesting feature or way of engineering your feature for you to for your models to learn from. So you can have 7-day means, 30-day means, or 30-day sums. These are all interesting ways of doing that. Then what we'll call cyclical time encoding. where you can look at cyclical time. The cyclical time is time that, changes, um, cyclically. So, for example, if you want the value to be one every 24 hours, the value will move from 0 to 1, right? You can use cyclical time encoding, and normally the functions you use are sine and cosine functions because these functions are cyclical functions, right? The only thing is that you ensure that you match the period of the sine or cosine with the period of the time scale that you want to use. So for example, if you want something that cycles every day, every 24 hours, so you see, we have now used np.pi, which is pi is 180 degrees, basically, right? We and then 2 pi is 360 degrees. So this is 2 pi, which is 360 degrees. That's a complete cycle. So a complete cycle divided by 24 times the hour. So that means you have essentially converted hour and the hourly time, part of a feature into a cycle that every 24 hours it goes around the whole sine wave or the whole cosine. So these are all very interesting ways of feature engineering. We talked about turning text into numerical representations. So first of all, you have to do the text cleaning and pre-processing so that text will match, right? You remove punctuation so that punctuation doesn't, change, how the text is encoded. You remove stop words and you do lemmatization. So these are all ways to kind of standardize the text, so that text will be the same. If someone were to say come or coming or came or all of them they can all be standardized into just a single stem word, which is a come, right? So that with this, it is very easy for you to kind of words are similar, even though there are small variations in the grammar and so on. We're not really interested in those variations in grammar and so on, right? We just want the root word. So that is the value of this process. Now, those were things we used to do in the past. These days, we use word embeddings, which we'll talk about shortly. Then we have bags of words, simple and effective with a small vocabulary. So if you have a small vocabulary, you can use a bag of words. So you do a vectorization based on the count of those words, right? And, use that to also represent your features. Then you have the TF IDF. The TF means term frequency. IDF is inverse document frequency. So what this basically means is that for words that are more common, you weigh less, while the words that are less common, the rare words, you weigh them more because the rare words tend to affect the meaning of a passage or a paragraph more than the common words. Common words like a, the, in, is, and so on, right? But rare words are the ones that have impact. So again, these were just like very simplistic methods for natural language processing in the good old days, right? Before we had neural networks that could be trained with NLP, and neural networks can now do embeddings, which we're going to talk about embeddings as well. We have n-grams, which is yeah, just capturing sequence of words. And you can see this uses the TF-IDF as well. Then embeddings, which I just mentioned. An embedding is basically a vector. A vector is a list of numbers, a list of floating point numbers, numbers that have lots of decimals, right? So, and it can be very long. It could be as long as 300 and something, you know, numbers in a list that represents a single word or meaning of the word, or 700 or thousands, 3,000. I've seen embeddings that, are up to 3,000, 7,000, dimensions. So when you hear of dimensions in the context of embeddings or an embedding vector, we are essentially talking about the number of numbers, the number of floating point numbers in that list that represents our word. And embeddings don't actually represent words. They represent the meanings that the words convey. So you may actually have several words that are totally different in spelling, or length or so and so on. But the embeddings are similar or close because the meanings of those words are similar. So that's what embeddings are. So yeah, we have word to vec globe and bet embedding. These are like libraries that help you to do simple embeddings. But these days with large language models, we now use um neural networks to generate embeddings. So I'm going to also touch a little bit on that. Then after that, we talked about feature selection techniques, how to choose, and there are different ways to do that. Um, ensure that you choose features that matter, ensure that you choose features that um, don't have uh, co correlation across, between them, right? Ensure that you pick features that impact the prediction as much as possible, right? And all of that. So there are methods to do that. We have different filter methods. We have the variance threshold. Um, we have correlation analysis. We have wrapper methods like the RFE, recursive feature elimination. So this is just a process of recursively eliminating features that have little impact on the accuracy of a model. So you can see here it uses logistic regression to test the features, right? And it basically will remove a feature and see if how much of the performance of the model is affected by removing that feature. If the if the performance is not affected that much, then it means that feature may not really have been that important. You understand? And it just iterates like that recursively until it narrows down to whatever number of features you want to select. These are all things we can do sklearn. Then you have embedded methods, right? Where embedded methods are the ones that the model itself will determine which features matter. So last is a good one. Last is actually a L1 regularization. We are going to talk more about regularization next week. And then we have tree-based feature importance. So that's kind of quick run through of that. I'm now going to jump into a bit of hands-on, right? Just to show you some of the things you can do, um, you know, in the context of feature engineering. So give me a second. So we will start with, you know, as usual, we will use our Jupyter notebook and try out a lot of different things so that we learn in the process. So first of all, let me create a new collab and we'll call it feature engineering. So let's try some very basic stuff. I'm going to start off first by trying to um, use a little bit of pandas, right? Just some of the basics. And there's a whole lot. The time in this class is not enough for me to do all of the data cleaning that is possible. It just isn't enough. So I will just see how we can do a bunch of simple. So I'm going to just go to Kaggle and look for some you know dirty data sets that we can use, just to learn basic cleaning stuff, right? So we can start with this one. So, um, here's the data set just to show everyone. Um, let's just see what we can do. So this is dirty data set that we can use to practice data cleaning. So I'm going to just import um, NP. Let's start with pandas, and then we are going to import um, numpy, matplotlib, seaborn, cargo hub. So now, so for me, um, to load stuff from cargo. So I'm going to first of all try to load this, right? So data path equals cargo hub dot download dataset download, right? Then I'm going to copy this path starting from datasets. So you can download directly from cargo just by dataset download, and then you come to a dataset and you ensure that the URL starts with cargo.com/datasets. Then you can copy from here, which is the this is the owner of the dataset, and this is the name of the dataset. So you can copy that and you put it in here, and then you just run that. Now, the interesting thing is when you run this, it's going to actually download it. Okay, so what I normally do is when I do this, I will try to, so 100% it has downloaded it. And when it downloads it, it's going to be visible, right, in this folder, in this same folder, right? But, or rather in this data path that is given to you. But the name of the file is what I'm not always sure of, but normally it's the name of this file, but instead of dashes, it has underscore. So the actual file name will be um, data path, right? Um, I don't really know what it is, but I assume it's this. So normally what I do is I will just first of all um, just do try to view the directory, right? So I can import OS and then do OS dot list dir. Then I specify the data path. So that will just allow me to see what is in that. So I actually see my file one.csv. I don't know if that's what it is, but if you do look here, you'll see the my file one.csv. So it does look like that is the correct file. This is my file one.csv. So, and that's what I saw here. So I can also just copy this here, my file one.csv, and and that's a file name. Then I can load that file into pandas by just read pd.read csv. Since then I can just use head tf.head to read the file. So you already see this is the file. Now, the first thing that you may want to do is, okay, let me do a bit of analysis to know, how many dirty, sorry, how many missing data. You already can see there's a none here, right? There's a none. So it's likely that you have a bunch of empty files. The first thing you can just do is with pandas df.info. Remember, pandas is like your first thing that you start off with, right? It's the first thing that you start off with. So you see that there are 11 columns. Well, okay, starts from zero. So 11, rank, peak, all-time peak, actual gross. So there's all of that, right? And memory usage. Now, if we want to do analysis of this, right? And basically, how do I check the number of nulls, right? There are many ways with pandas. One way is to just say df dot is null, okay? Um, so let's look at that first. So df dot is null gives you false if it is null. Sorry, if it is not null, and gives you true if it is null. And that gives you for all your columns, okay? So you can then go to each column and like for the rank column, in this case, I just put the column, you know, um, so it's going to give me that same information, but only for the rank column because I only specify the rank column. I basically, what is null does, it gives me true or false across the entire data frame, right? Then I can now select which column I want by using this column index. So you see that now I can then do count, and that tells me the number, you know, that are null. Let's try this with another column, peak. Let's look at the peak column. The peak column, we have a few of them that are null, right? Um, so count will still give me 20. But if I want to filter and get only the ones that null is true, then we have to do what we call a mask, right? So to do what we call a mask, we can essentially do this with pandas. Okay, equals true. And so this is really just going to return this. We're now using this condition as a mask. In pandas, a mask is basically um, a condition or an expression that you use to filter out some rows or columns. So this is, let me start off with just that only. So you are going to see that um, it's only giving me the columns that is null is true. That's why you have nans here, right? If I change this to false, it's only going to give me the columns that is null is false, right? So yeah, but a couple of this also has none, and that's because um, it's giving me the entire row, right? So not just one column. So, but you could always do something like this. You could pick a column like rank, for example, and still apply this um, rank. Yeah, you can't index a series. So this will only give you the columns that are null, the rank columns that are null, and there isn't any. So it gives you all 20. Pick. There are a few pick, right? Um, okay, so I think I missed this is for the whole. If I want to get for pick, I have to do only for pick. So I will do pick where df um, okay, so um, this is still a mask that says, okay, I am picking the pick column, and then from this pick column, I'm finding where the pick column is null, right? So again, it's kind of the same thing is indexing. So this is the one where null is false. So only the ones where it is not null. If I say null is true, to give me the ones that are null. And then if I do a count, it will give me the actual count. So this is the one that count wasn't correct. So so anyway, this is a way of inspecting it, right? Now there are more there are other ways you can just inspect this, right? Or just do entire statistics with um with pandas. So apart from its no, we also have its NA. So you could do df dot is NA. So again, this gives true and false, and it's almost basically the same thing. Then if you want to count nulls, so you could just do a df dot is NA dot sum, right? So this is going to give you a kind of list for each column, the number of NAs in them. So you can see that peak has 11 and all-time peak has 14. So that's one way of doing it. And there's so many different ways of doing this. So we're not really going to I'm not going to explore all of them because there's so much for us to do in feature engineering. So I'm going to share some material. I think I did that already, but I can share some material on how you can use pandas to do a lot of these things. Okay. I'm going to look for that material. Okay, so the other thing you can do is um you can remove rows that have these um n- nans, right? You can basically just use drop na. So let me show you how you can do that. So did if I did if I did df dot drop na, drop na is going to drop all the nans. That is all the nans. So you can see basically what drop na does is it drops every row where there is a single na in it, right? Where there's a single na in it, you can drop. It drops every single row. So even if there's just one na in a column, okay, or one nan in a column, it's going to drop it. So now the interesting thing is I could say, okay, I don't like there's so many nans here. Why would I want to drop all of this column, all of these rows just because of this? So I want to specify that I don't want to drop um for this one. I want to ignore this. So there is a way you can do that. You could say drop now. Then you drop now takes a bunch of additional um, you know, parameters here. So for example, um you can have an axis, right? You can have a threshold, you can have a subset, you can have in place, right? So let's try something like subset. So subset is which column do I actually want to consider when I want to drop, right? So if I were to take in this case there is no age here, so let's say I don't want to drop from this all-time peak because I can see there's a whole lot of nans. But let's say only the peak, right? So I'll use peak as a subset. So when I do that, um, let me just show the data frame again after doing that. So you see that the everything that has nan in the peak gets dropped, but there are a few nans in the all-time peak because I just said only drop from the subset, that has peak. So this allows you to control. If you want multiple columns, you can just put a list of columns here. So for example, if I wanted to drop where subset peak and shows, for example, then um okay, I missed something. Yeah, I should have just had a single list, single list. So, but because we don't have any nans in the shows, right? It doesn't really make much difference. So that's just quickly dropping stuff, missing values. The other thing you could do is you could decide, I don't want to drop missing values. I want to see if I can replace them with something useful. So, so axis means in which direction. So axis of 0 normally means row wise. In other words, you want to drop the rows. But if I say axis of 1, you're going to drop columns. But of course, this won't work because the subset now, I should change it from a column index to a row index, right? Um, let's say you are going to basically, okay, let's just leave this as it is. So you see that it's still kind of the same thing. Oh yeah, I did in place equals to true, which I shouldn't have done because that is modifying the value. I don't want to modify the value, so I need to reload this. Need to reload and have my original numbers back. Um, okay. Yeah, this won't work because it's in place, but this will work. So this will at least show what is getting dropped. So axis of 1, nothing actually gets dropped, right? But if I were to say subset is peak and axis is 1, it would probably drop that whole. Well, it won't because axis is a column direction. And if I want to drop the column direction, I have to specify the row as a subset. So let me just take out subset first for now in this case. So you find that it is dropping columns that have nans. And you see that the 2 columns that have nans are gone. So that's what axis does. Axis basically says either row wise or column wise. If axis is 0, you will see that it's going to drop rows that have nans. But if axis is 1, you can see here now what is left is just 1, 2, 3, 4, 5. Just 5 rows. 1, 2, 3, 4, 5. Just 5 rows. All the remaining rows had nans and they were dropped. Okay, but all the columns are intact. But if I change axis to 1, it's going to drop all the columns that have nans and all the rows will be intact. So the 2 columns that have nans were the peak and the all-time peak, as you can see. So that's what axis does. Um, but if I want to still do row wise, I'll have to use axis of 0, which I don't necessarily need to specify axis of 0. By default, the axis is 0. Then I'll mention the subsets, set rather, which the subset is basically telling me these are the columns I want to check when I'm checking for nans. I don't want to check all the columns. So I'm only going to drop the columns where there are nans, or I'm only going to drop the rows where there are nans in this column. So you see that if there's any nan in the pick column, that entire row will be dropped. So that's one way of kind of, okay, let's say pick, that's cool, right? I can remove anything. I don't want to deal with pick that doesn't have value, right? But all-time pick, okay, I can do something else with that instead of um let's say df2. I always df clean instead of instead of you know dropping all-time pick that is none. I want to zero those ones. So with that, you use fill now. So fill now is now df clean that I want to clean. I use fill now. So fill now is fill the not applicable or nonce with a value. And fill now you typically have to specify a value. And if you specify a fixed value like zero, everything will be zero, right? Anywhere where you had this none will be replaced with zero. So you can see that here we have 1, 2, 3, 4 nuns. So if I do that, those 4 nuns become zeros. And in most cases, that's the most logical thing you want to do, right? If there's no value, we can assume that it is zero. But in some situations, it may not be. So for example, we talked about a case where, okay, the age of children in a class. So if the value is none or not available or none, does that mean that the child is 0 years of age? No. So maybe the best option is let's pick an average age, average age of the class. So you can now use fill now, you can use the average. You can do something like df in dot mean. You need to get the column first. So all time in this case, let's assume that that's the age. That dot mean. So I want to fill it with the mean age. Okay. If I do this, can only concatenate string. Okay, so this is still another problem that came because we did not do proper data cleaning, right? Yet. So that's because all-time peak is actually not a number, but I'm trying to calculate the mean. It's not a numeric field. If you look at where I did this, right, it says it's an object. And the reason why it's an object is because you have these funny brackets in there which are not numbers, right? So, okay. So, but if it were a field that were numeric, like number, I could use mean. So that's another question. Okay, is this how we really want this data to be? Maybe there's some more cleaning that we can do here, right? So those are some of the things to think about. There's a whole lot of stuff you can do. Unfortunately, this class is not really about pandas data cleaning. That's a whole different course that we have done. And there's more you can get from there. Others you can look at, the other things you could look at is duplicated, right? Duplicated will give you a list of, you know, duplicated fields, right? So let me rerun this because it does look like I had, um, I had changed that data set. So yeah, so okay, duplicated is giving us per row. So the fact that it has false all through means there's no two rows that have been duplicated. So typically in pandas, if a row is duplicated, it means that every single value for that row in every single column, right, matches another row where you have every single value in every single column being exactly the same. So if you do find any rows that are duplicated, then you can just do drop df dot drop duplicates, right? And this will remove duplicates. But of course, since we didn't have any duplicates here, you are getting back exactly the same thing. Then we have rename. Rename is used for renaming columns, right? So there's a whole bunch of other stuff that you can do with pandas. I had shared something before. I'm going to point us back to it. Data wrangling, data cleaning. That's just the first step, right, in feature engineering. Now, when you are done with data wrangling, data cleaning, you still have to do other things, right? So it's not enough to say, oh, okay, I have cleaned the data, I've removed all the NAS, the NANs, and all of that. But um, you would have to do things like, transformation. After cleaning, the next thing is transformation. So what is transformation? Um, so like we said, there are two types of transformation. Transformation basically is converting that data into a numeric format that allows your model to learn from it. Remember, models can only learn from numbers. Most models, anyway. There are some models that you can just give them categories and they can handle it, or some other kind of, data structure. But most models learn from numbers. And in all of what we've been doing in the past, we've just been using training models with data that has already been kind of transformed already, right? It is not, we didn't have to transform them. So typically, there are many things you can do when you normalize, and there are many, many reasons you may want to normalize. So the first thing is, if it is numeric, you can do standardization and normalization. So for this, I'm actually going to show us a good example of the impact of standardization and normalization. If you remember, there's a task that I gave, the linear regression with multiple variables, okay? And we actually tried to, let me see if I can grab that data set. All right, that's still a Kaggle data set. And we found that there are a bunch of numbers that were very large. And I did a bit of experimentation. Maybe I should just open my experiments here. So I did a bit of experimentation and task one answer. So I did a bit of experimentation just to show if you do this with um, normalization and without normalization. So I actually ran this regression without normalization. And then I ran regression with normalization. And I'm going to show you the difference, right? So let's first of all just take the data set, not question one, but question two. So the data set still comes from Kaggle. So we are still going to just load it. I'm going to put it back in here so that, so this is data set. If you look at this data set, you see that the age has an order of magnitude of tens, right? The experience has an order of magnitude of ones, right? The income has an order of magnitude of thousands or tens of thousands. So already that is three different scales. Now, if you train a model with just this, and I'm going to show you because I'm going to run that here. We will see this is regression without normalization. So in this case, I used 1,000 epochs, okay, and I used 0.001, which is a very low learning rate. If I use a very high learning rate, it probably would blow up, and it did. So yes, I got this. This wasn't, you can see that it did not converge. You see how all these points are scattered. This is the correct line of prediction, right? And see how all the points are scattered. That's the first thing you notice. The second thing you notice is that The cost is very high, right? It starts from a really high value. And when we printed the cost versus epoch, it starts from 1.75 raised to the power 9 times 10 raised to the power 9. This is a very high cost. It drops, it comes down here. This looks like a low cost, but it's not. It is still, the final cost is still what? 48 million, right? Very large. And then my parameters are also very large, which is not really a problem. But this is 1,000 epochs, and we did not converge, right? Now, how many epochs do I need to converge without normalization? So let me increase this to 100,000. 100,000. I'm going to run this again. And yes, it's going to take 100,000. Right. So you see, I need about 100,000. It's now better converged. You can see the red dots, which are the predictions, right, are closer to the blue line, which is the true line of correlation. Right now, let me run it for 500,000 epochs. So you can see I have to increase epochs to compensate for not normalizing. Okay. For not normalizing, I have to increase the epochs. So this is kind of trying to show a practical benefit of normalization. So I think I picked 500,000. So it's almost there. So you can see, okay, yes, it's kind of now looks like it's good. The final cost, this is actually a final, you can't get less than 1.5 million as the cost if you don't normalize this, right? And you run it. No, if you run this for like 1 million epochs or 5 million epochs, you will still end up with a cost of 1.55. So it's kind of converge at this point, right? But look at how many it took. Now, let's go and normalize. I now normalize everything. I normalize both the inputs, the X values, and the Y values. Okay. And I'm still going to run it for 1,000 epochs. Take note of the learning rate now. Learning rate now is 0.01. By the way, if I used 0.01 here instead of 0.0, I had to lower the learning rate because the gradients are so large. See the gradients, the cost is large. If the cost is large, the gradient is going to be large, right? So the gradients are so large, I had to lower the learning rate to 0.001. If you increase the learning rate, let's run this again. And I'm not going to go to 500,000 because of the time. So I'm just going to go to 1,000, right? A higher learning rate. Now, you will see that we have hit nans. We hit nans because I just increased the learning rate to 0.01 and I have blown up my gradients. The first was 1.717, well, is it 17 trillion or 1.7 trillion or something? Yeah, 1.7 trillion. The next one, it just goes out of range. And then after that, we have infinity. Then after that, we have nans. So it basically did not train. It basically didn't train because I did not normalize. So because I didn't normalize, right, I still want to train it unnormalized. I have to compensate by lowering the learning rate. But when I compensate by lowering the learning rate, it takes longer to converge. A lower learning rate means it learns slower. So it takes more epochs to converge. So 1,000 epochs still does not converge for me. You can still see the predictions are scattered all over. Now, conversely, I did a normalization. I can go with alpha of 0.01 because I did a normalization. So remember, I've done a normalization here. The same 1,000 epochs, right? This is it, right? I normalize the values. This is standardization, by the way. Standardization, even though I call it normalization, but this is the standardization is when you subtract them and divide by the standard deviation. So you're going to get it um, 0 at mean with a standard deviation of 1. That is how you get standardization. You subtract the value from the mean and you divide it by standard deviation. So I have standardized both the X values and the Y value. Okay. And then I run it for the same 1000 epochs with a higher learning rate that was blowing up when I didn't standardize it. And now look at what it looks like. We converged very clean in the same 1000 epochs. And then we have a cost that is very low. Of course, that's because we standardized. So the gradients are very small, right? So there's no gradient explosion. That's why you can go to a higher learning rate. But because you can go to a higher learning rate, you can also converge faster. So this is one thing that I know a lot of people didn't know this, but I know a bunch of people also knew it. But I just wanted to let you know the impact of normalization. But the thing with normalization, which everyone needs to understand, is that when you are normalizing, you have actually changed the values. You have changed the data points. You've changed the values of the X and you've changed the value of the Y. So when you want to predict again, you are not predicting into. So for example, now remember, we're trying to predict income based on age and experience. Okay. So how do I now predict if I'm given a new value of income? I have to remember the scaling factor because if I do not remember the scaling factor, I will scale differently and my model will give me a different answer. And when I even descale, right, I'll also descale differently. So this is one thing everyone needs to be very careful of and pay attention to, that when you are standardizing or normalizing, right, if you want to predict on a test set, are you going to use the standard deviation of that test set? Or are you going to use standard deviation of the entire population? Are you going to use the mean of that test set? Or are you going to use the mean of the entire population? Right? So you have to maintain the constants that you used for standardization to de-standardize, if I may use that terminology, right? To convert it back. So if I now give you a value and say, my age is 51 and my experience is 7, right? And I tell you, tell me how much my salary will be. Or, okay, so how will you do this? That's why you see I did this to predict with denormalization, right? I now have a new set of values, right? Um, or predicting for new values from a test set. We still have to use the same factors to normalize and denormalize. So I have to remember the standard. So I now have a test set, which I just simulated here, 34 years, 23 years, 51 years, and years of experience, 382. I want to predict my income. I cannot use the standard deviation of this test set because it will be a different scaling factor. I am now scaling it into a different distribution. So when I use that and I use the same model to predict, I'm going to get the wrong answer, right? Even if I denormalize, the answer by multiplying it. So you have to remember, so what I did here, I am now using the standard deviation of X1, not the X1 test, but the training value. That's what I'm using. I'm using a mean of the training set. So I'm using the same factors that I used to standardize when I was training. Is the same factors I will use to standardize when I'm testing, right? This is very important. And then when I want to give the actual value of Y, I have to convert it back, denormalize it basically by multiplying it by the standard deviation of the Y and the mean, add it back to the mean. So I get back the correct values. Otherwise, I will not get the correct values. This is very important. Now, this brings me to the third part. So if it is going to be very painful for me to maintain, like if I'm training a model and I don't even know the data sets that I used to train it when I did the standardization, how will I know what factors I used to standardize to be able to, so in this case, you can say, okay, let's just standardize only the X values. It makes sense to say, okay, I don't want to normalize the Y. Why? Because if you look at your formulas, right? Remember what is blowing up is the gradient, dm1, dm2. dm1, dm2 depends on loss and X. So if I standardize X, right, I can reduce the impact of the gradient. The loss is a second thing. The loss depends on Y pred minus Y train. So if I don't standardize Y, it doesn't make much difference because remember the loss is a difference between them. So even though the order of magnitude of the actual value of Y and Y pred is high, 30,000, 25,000, but the difference might be very low. Not that much, not that low, maybe 5,000, right? But the difference is low enough that even though I do not standardize the output, right, or the Ys, but because I've standardized this, it does reduce the gradient enough for me to converge. So can I prove that? Yes, I can prove that. So instead of now, I'll do the same thing. Instead of normalizing Y train, I just make Y train Y. I don't normalize it or I don't standardize it. And then let me rerun this training. Still the same alpha and the same epochs. Will it converge or will it not converge? Right. And I run this. And what? Voila. It converges. There's really no difference between this, right? Even though you can see that the C is now a large value because I did not normalize M1, M2. Sorry, I did not normalize Y, right? But this make more sense. Now, if I did normalize Y, which is what I have here, right? And hold up. And let me rerun this, right? Rerun this just to be sure that I'm not lying to you. See the M1, M2, C. C is now a really small value, 5.5 raised to power minus 17. Basically, this is zero. C is zero. M2 is 1.0, M1 is minus 0.1. If you were to rescale them, right, you probably get the other one, but you still get the same almost convergence here because the predicted values are so close to this line. That is the actual true correlation. But if I say no, I don't want to do because I don't want to have to think about how do I you know denormalize when I am predicting, right? Then if you now look at your constants here, right? But you still have the same quality in terms of how close our prediction is to this. The final cost is now 1.54, which is the same as I had when I ran this thing for a 500,000 epochs, right? If I run this for 500,000, okay, let me just, did I run it for 500,000? Let me run it for 500,000 or 200,000, right? 200,000. Okay. This is just a different one. You can now see the loss will be the same. You can see it's approaching 1.533 million. 1.533 million, right? That's the same cost as I got. Here is 1.551. So it's about the same cost, right? Even though the parameters are different, right? So this is an interesting thing with standardization, and normalization does the same thing. So this is kind of a graphical you know um um demonstration of the impact of normalization. Okay, so let's move because we don't have so much time. So the other things you will do as part of feature engineering, um, standardization, normalization. So like I said, for standardization is basically subtract the mean and divide by standard deviation. That's standardization. Normalization is subtract each value is um, subtract from the minimum value and divide by the minimum value minus, sorry, the maximum value minus the minimum value. In other words, it's basically how far is this data point from the mean divided by the range. In other words, within the range of values in that particular feature, right? The data points for that feature, right? Where is the position of this one? So you are basically rescaling everything to 0 to 1, like I said. So the minimum value, if you look at this formula, right? So it's basically um xi xi minus x mean divided by x max minus x mean. This is what normalization is. So what it means is that the minimum value will be at 0 and the maximum value will be at 1, right? That's what normalization is. So I want to see if I can put this into like a formula kind of thing. And it makes sense. Okay. So yeah, xi minus x mean frac dfrac xi minus x mean, okay, divided by um x max minus x mean. That's basically it, right? Um, x max. So did I miss something? Silence. Okay, I did miss something. So this is normalization. It's basically scaling, right? So the question between standardization, each of them have their own role, right? So if we look back at the what I was saying, you normally would use, let's see if we can go back there. Um, you use standardization for linear models. You use standardization for logistic regression. You use standardization for neural networks, and use standardization for SVMs. But you use normalization like where you want to have 0 to 1 values, right? Um, 0 to 1 values. Okay. So it depends on your usage, actually. If I'm to answer that question, which one is better between standardization and normalization? Over time, you can experiment, you'll find out. Okay. Is it always that the least the cost, the better the model? Yes. The lowest cost, the model that has the lowest cost, yes, is the better. It's a minimization problem. If you can get the cost to 0, that means you have a perfect model, right? But that will not happen because your data is not perfectly correlated. If your data is perfectly correlated and you have a model that is good enough, then that model will have a cost of 0. But no data is perfectly correlated. So that's the thing. All right. So now the other things you can do as part of feature engineering. So we talked about normalization and standardization. Yes, I was going to also let me put this in here as well so that we can also so standardization. So standardization is kind of the same thing. You will do um basically um it's going to be xi minus mean of x. Okay, we can just call that x mean, right? Okay. And then divided by standard deviation, basically. Um, so that's you can just say standard deviation of x, right? For that particular feature set. Okay. Yes. So that is standardization. So um, the difference is that standardization is going to give you values from 0 to 1, right? While normalization standardization is going to give you values centered around 0, right? That can go higher than 1 sometimes, but most times it kind of goes to 1, or it goes down to because it's xi minus x mean, right? The mean is more or less like in the middle. So you're going to have positive values above 0 and negative values below 0, right? That's what standardization will give you. But normalization will give you values that are in the range of 0 to 1. So you ask yourself, which of these ranges does best for my model? That's what determines what you use, whether you use standardization or normalization. Now, if you are doing, and it's very easy to do this with sklearn. Normally, of course, you can even do it NumPy. There are so many different ways of doing this. With NumPy, I think a bunch of people did this already, right? NP dot, you can just say X standard is NP dot is X, basically X minus X mean um over X. I don't even need to, well, you could do the X mean, X dot mean, or NP dot mean X. Whatever gives you the mean of X along a particular axis, right? Typically axis would normally be 0, right? Over NP dot STD, standard deviation of X, right? Or if it's all of the X's, right? This is a this is for the case of um a vectorized X, right? So that will be X norm. You can let's use norm, even though the norm, you know, um, so that's it, right? Something like that. And sklearn has its own way of doing it, so many different other libraries, right? But if you're doing a normalization, it's basically like I say, you can do X norm. So you can see this does it for me. It's basically X minus the minimum value of X along that same axis over the maximum value of X minus the minimum. So it's the same. You can see that's Xi minus X mean over X max minus X mean. That is this, right? While standardization is this. So I think I can just cut this and put this in here and make it look nice. And same thing here. Okay, so that's it, right? Um, so now the other interesting stuff that you may want to think about would be apart from these are for numeric type of fields, right? But how about for fields that are not numeric, like fields that are like categorical. So you still have this kind of thing that you would do with categorical type of fields or values. So let's talk about that. That's very interesting because that is where you will, I don't think a lot of people have encountered it, right? So for categorical, so when we say categorical, what do we even mean? So let's assume you have categories. So let's take a simple category, right? Um, let's start with the simplest one, right? You say gender, right? Gender, okay, we say male and female, okay, right? Now, these are just words. How do I convert this into numbers, right? If it is a binary class like this, so you have what we call binary classes and classes that are non-binary, right? So a binary class has only two members. Or a binary class or category, well, you can just still call it category, has only two members, right? So examples are, yes, yes, no, male, female, boy, girl, all of that. You know, even things like, you know, um, big and not big, right? Or big and small, right? Big, small, you know. So these are good. These are binary categories. So for binary categories, it's very easy. You just assign one of them a zero and assign the other one a one. So it's very easy. So when you want to normalize this one, you can just say, you can write a code that says um, X gender would be something like, um, well, okay, so this is saying NP random of choice, but I've just said something like, um, you know, X gender, if the gender, is um equals male. This is assuming you have first of all cleaned up the data so that all the males will be the same spelling, because if not, you have a problem, right? Um, so it will be something like um one if X gender equals male, else zero, something like that. So it you have now transformed it, even though this is not exactly how I'll do it, right? But this gives you an idea. You can loop this, or you can use what do you call it? No, this is not one hot. I'm coming to one hot. So for binary, basically you give one to one class and then you give zero to the other class, right? That's it. Okay. So this is typically simple binary encoding for categories. Now, for categories that are non-binary, right? Non, binary categories. In other words, categories that have lots of members, right? So a good example is color. Color would be the category, right? The members of color would be red, blue, green, yellow, you know, orange. So this is a category has lots of numbers. So this is where you use multiple methods. There are three methods that were mentioned. One of them is one hot encoding. So a one hot encoding, right, is this. You take you create a vector called a one hot vector. And this vector is going to have the same length as a number of categories, which the AI seems to have figured it out, right? So let's assume, you are basically going to do a list, right? A list. So let me make it in simple stuff. A list that the length is, the length of categories, right? And this list has to have zeros in it. Okay. So let's assume categories is this thing here that I had here. So we could say, okay, categories. So you have this category, red, blue, green, yellow, orange, right? So the one hot vector is going to have this. So if I run this, you have how many categories, how many classes in the category? You have one category called color. And you have how many classes? One, two, three, four, five. You have five classes in the category called color. The five classes are red, blue, green, yellow, orange. So you have a one hot vector that has five elements in it, five numbers, 0, 0, 0, 0, 0. And you would normally give them values of zero, right? You give them values of 0. Then what you now do in one hot encoding is um this is a positional encoding, like I said. So that means that this position 1, right, matches with red. Position 2 matches with what? Blue. Position 3 matches with green. Position 4 matches with yellow. And position 5 matches with orange. That's the thing. So this is already encoded. It's part of your code. So if you change the position, it totally makes one hot encoding irrelevant. So in this case, right, a category that is red, okay, red will have which encoding? Red will have 0.0, sorry, it will have 1.0. Then the rest will be 0.0. So why is this so? 1, 2, 3. I think we got all the 5 now. Because one hot encoding says that the one category that applies, that position will have the value of 1. That's why it's called one hot. Hot means, what is hot is the one that is hot. That is, this one is the value. This is the position that corresponds to red, right? And therefore, it is, so let me even, like, X, if we're to say something like DF red, DF, um, the one that is red would have this encoding, right? And if it is blue, this doesn't really make sense. It's code anyway, because I'm talking about entire columns here. But let's call it, okay, let's say X red, right? The X that is red, not a data frame, but let's just say an X that is, the one hot encoding of an X that is red will be this. And the one hot encoding of X that is blue, what do you think it would be? Right? Because blue is the second position. We'll now put the one here, right? And it goes that way, so you could just say X equals just a list of numbers, red, another red and blue. Well, okay, it should actually be a dictionary if I want to go with this, right? So, and we're trying to figure out what the one hot encoding is. Okay, so, or we could just say it's an empty list first of all. So, sorry, an empty dictionary. So this is blue. This would be green. Green would be here. So this is the one hot encoding basically. It's just saying the one that is hot will get the value of 1. That's really what it is. So if you adjust the position of your classes in this vector or in this vector mapping, then your one hot encoding will not work out again. So you have to maintain that consistent positioning. And that means whenever you are doing one hot encoding, you have to make sure you consider all possible classes in that category, so that if you have to introduce a new class in a one hot encoding, it becomes a problem. So this is a one hot encoding. So with this now, you can then use this to just encode. And a simple way of doing one hot encoding, right? There are a lot of um, you know, it's something like I think there are simple things like, okay, X of um color would be something like you would first of all do something like this, maybe like what we did before, 0.0, right? Times length of categories, or which we had already called it one hot vector, so we can just say one hot vector. Then you can now, in this one hot vector, you find its position. and then you can say X color, the position, right? So the position you would now find the position in the categories that categories dot index. Let me just use some kind of uh that is it, right? So you find the categories, you find the index, right? In this one hot vector that the position matches the color that you want to do, and you assign that one a value of 1. So you always end up having the value 1.0 in that particular position. That's one hot encoding. And if you go look at sklearn, and there are, a lot of simple libraries that, or simple functions that do that. So you don't need to actually crack your brain about this, trying to figure out, oh, how should I do this one hot encoding? In fact, with um with sklearn, there's a simple way to do this, right? It's just called one hot encoder. That's basically what it's called, right? You just do one hot encoder and you call it. That's it's very simple with sklearn. Let me show you how you can do that. I actually have the code here, so I'm just going to do that. So you already have pandas thing. You just import a one hot encoder, right? And you give it a lot of this thing. So when you want to encode anything, you know, it can actually generate a whole stack of one hot encodings for an entire data frame, right? So you don't need to be doing it manually by yourself, right? So you can figure out how you can do all of this. Okay. So that's one hot encoding. Now, apart from what one hot encoding, we have what we call label encoding. So label encoding, if you want to go with these same categories, right? What you would have done is you would give them numbers. So red would be 0, blue will be 1, green will be 2, yellow will be 3, orange will be 4. So in that case, what you would do something like this. Um, Basically this, right? Except that it would not be a set of vectors, right? Rather, it will be a set of actual numbers. So red will check, okay, red was the first one, so its value will be 0.0. Okay. Blue is the second one, so its value will be 1.0, right? Green is the third one, so it'll be 2.0, right? And so on. So you're just assigning them numbers. The danger with this label encoding is that because you have basically arbitrarily assigned numbers to these things, it tends to, you have created a kind of ordinality here that orange is greater than red. You understand? If if there's no ordinal relationship between orange and red, then this is the wrong approach to use. Okay? So it's only good for ordinal data, right? Ordinal classes, right? Or classes that have an ordinal relationship. So a good example would be if you had bucketed. So by the way, another thing is when you take a numerical field like age and you bucket it into groups, right? Those groups become categorical. So a good example of using ordinal, right, of label encoding is bucketed age groups, right? So let's assume you created 3 age groups. You call them children, then you call them adults, then you call them seniors. So now you've created 3 age groups, right? So typically this shouldn't be a problem, right? And these 3 age groups, you can now bucket them. So when you bucket them, you put people in these ages, you can then assign ordinal labels. So you could say children are 0, right? That is their, adults are 1, right? And seniors are 2. You will not really have much problem here simply because there's actually an ordinary relationship between these categories that you have created. So this one is okay. Then the other type of encoding that you can do for categories is what they call the target encoding, right? So target encoding, we have frequency encoding and target encoding. So those are additional things you can do. Frequency encoding is when you have, oh, by the way, you can also do label encoding with sklearn. It does that for you. So it has what we call a label encoder, just like we had a one-hot encoder here. So you have a label encoder which you can just use for things like that. Then for frequency and count encoding, you can also use frequency and count encoder, right? This also works. Okay, so you can use a frequency and count encoder, right? And for frequency and count encoding, um, you just calculate the frequency of occurrence, right? So that is, this is a good case, like a category which is like cities. Okay, so cities, you count the number of occurrence of cities, and you can use that, right, as the encoding. Then we also have target encoding. So target encoding is basically just replace the category with the mean of values, right? That's in the target, right? The target being the Y values or the labels. Okay, so you use that. So those are all ways you can encode categorical information. Then the other things that you may want to think about, okay, how do I encode as well? Is date. Okay. And we talked about a lot of things in dates, right? Um, I did mention binning. Okay, I've mentioned binning as well, but dates is another thing that but most of the time, dates, you just encode them as numbers, right? You can encode them as numbers, and use floating point numbers, a number that represents the timestamp, okay? And then when you use the number that represents the timestamp, then you can just normalize it later on or standardize it. So after doing that, then we have what we call feature creation. So feature creation is when you want to add some new additional features just to make your data a bit more rich, right? So there are different things we talked about in feature creation. So a good example is um, mathematical transformation, where you can have um, things like debt to income. You can have division, subtraction, and multiplication. So this is a good example, right? You have what we call ratio, mathematical. So in mathematical, you have ratio. Ratio is just a division, right? And then you also have difference, which is just a subtraction, right? Which is just a subtraction. Then you also have a multiplication or product, right? Which is just a multiplication. So um, then we have polynomial features. So polynomial features, right? Um, you could, for polynomial, okay. So for polynomial features, right? Let's assume you got a data set, and part of the features would be like, okay, the let's say the rainfall or the size. Okay, let's say you want they give you prediction to kind of predict the amount of um gas that is emitted by um you know vehicles, for example. And one of the features will be the distance traveled, right? Distance traveled by the vehicle in a particular period of time. So distance travel is good, right? But we may also find out that the speed, of the vehicle also matters, right? In terms of emission, right? Not just the distance traveled, but also the speed at which it traveled, cover that distance or the acceleration. So for a feature that, okay, they give you distance traveled, and maybe that is kind of maybe X, right? So you you may want to create additional features to represent speed and acceleration. So you could square the distance traveled. So if the distance traveled is d, you could say, okay, let's square it, right? D squared, right? So d raised to power 2, right? You could also say, okay, let's even include um okay, distance squared is not the speed. Distance squared is the area. So okay, area. You also want the speed. So for speed, you would do square root of d. So you could do a square root of d, right? That would be you know, the speed, right? Or d divided by time. But okay, maybe not square root, d divided by time. But you could also say, okay, let's divide d divided by period or time, right? You could also divide d by time twice, by time squared, right? So you are now introducing additional orders of, you know, that same parameter. And you can basically simplify all of this to just polynomials, right? So you can just use polynomials, add higher order features. So instead of just d, I can add d squared, I can add d cubed, right? Or higher orders of polynomials. And then, you know, the model will learn better because I've provided additional data that represents the order of magnitude. And with sklearn, it's really very easy to do that. You just use these polynomial features and you specify the highest degree. So if you specify a degree of 2, that means the highest order will be d squared, right? And then include bias could mean you can also add a an intercept, basically. That's what bias means. You add a c. Okay, so essentially you are creating a polynomial, not linear. Well, linear is a special case of a polynomial, it's a first order, right? So you can create multiple degrees. So yeah, so good example here is if you are given salary, you can do salary squared, for example, or other things. And then we have interaction features, right? Interaction features are where you combine different features. So if, for example, you are given um, features like, okay, the age, the income and the age, like what we did before, where we had income and age. When you can now create an interaction feature called income age interaction. And we still use that to predict. In fact, I would be interested in using this income age interaction to see if we can improve the quality of this multiple linear regression that we did for remember we used interaction and age to do this, right? Now imagine if I added a new feature called interaction age, sorry, income age, right? Interaction between income and age. And I created that and I use that to see if I can predict, even though that breaks the rule because you should really only combine independent variables. You should not combine the dependent with the independent. But yeah, that's just a good example of that, or an example of that. Then you have aggregate features, sums, right? So you can just think of feature engineering, additional things like, okay, let's add additional features that are sums and see if we can do prediction based on that. And then we talked about rolling windows as well. Rolling windows would be, I want to add additional values based on what we call, you know, um, moving averages, right? So you can have a moving average. A 7-day mean is basically a 7-day moving average, right? And then you have a 7-day standard deviation, right? So you are taking the cumulative value over the last 7 days. And these are really very nice for time series data, right? Because it time series data, the moving average extracts um, a trend or a pattern, while the standard deviation extracts um, instantaneous changes or spikes, right? So these are called moving averages. Well, averages, the standard deviation is not really an average, right? You know, are very useful. These are very useful for time series predictions, right? Because the prediction, you are basically decomposed that time series into a trend path and a spike component. And your model will be better able to, do something with all of that. In fact, it would be nice if I could plot a graph of this. So let me see if AI can just, generate time series, but I probably don't have enough time to do that. And plot moving averages and deviation, standard deviations. So that might be some kind of homework for everyone to do. Then we have binning and so on. So then date time, yeah, we talked a little bit about date time. You can convert date time, you can get the entire timestamp, right? But you can also decide to just take components of the date time. And this is very important in situations where um, you maybe there's a cyclical kind of relationship, right? So in cyclical relationship, maybe things that happen every a particular month every year, right? And you want to predict it. So you don't know whether this thing happens because it's always May, right? Or it's always June, or it's always a 52nd week, or it's always a 12th week, right? So you can create additional features based on cyclical time so that it will help to catch those correlations, right? And the model can learn them, right? So you have others, time since events and so on. There's a whole lot of stuff to do, right, with all of this feature engineering. Um, yeah. Then for text, I think I'll talk about text a bit more when we come to a bit of natural language processing. The kind of things, the kind of feature engineering you will do for text. So, but you have text cleaning and pre-processing, lower casing, removing punctuation. So bag of words, this is how you can do bag of words, right? Um, basically, we have what we call a count vectorizer. A count vectorizer is a very powerful feature extraction tool in sklearn that allows you to just throw words into this count vectorizer. And then after that, it will pull out and it will give you, stuff basically, to give you a list of, you know, the count of words in that. So of course, this is review. Let's see if I have words. So for example, let's take this store title or artist, which already exists in our data frame. And we can just say, tour title. So you first of all create a count vectorizer. Let me go check. I think I missed it. Tour title, tour title, tour title. So it's a lowercase t. So, um, hmm, um, I may have changed my data frame. Okay, no, I did change my data frame. I ran this other one. So let me just run this just to show us, yeah, my file zero. So again, so tour title is back here. Let me just show you how this looks like. So, if I run this and you see the X, you see it's a compressed sparse row matrix of this. Um, x dot um, there's a CSR matrix. So I guess um, I need to extract the value. I thought this was a NumPy array, but it's not. It's a model. So because it's a model, it fits thought title into this model. I probably need to do something like predict. Okay, it does look like well, it's still a row matrix. It's a matrix 2041. So we extract the values. It's going to give you a kind of um a count vector matrix. Basically, correlation between words. Okay. Um, then we have a bunch of other things. TF-IDF, which we can also do here. Yeah, same thing. We will use a bunch of these later on. So again, this also gives us the same sparse matrix. And then we have n-grams, and then we have embeddings. So embeddings is a topic for another sec another session. Then we have filter methods, how you can do feature selection, right? Um, so this variance threshold is basically a way for you to calculate, right? Um, or to select based on a threshold, basically the variance, which is the variance is square of the standard deviation. So you will drop features that don't have that much variance. So a good example is if we were to train on um if we were to train on let me just take this same one. Let's say actual gross. So actual gross df numeric. Um okay, I don't want to just take I'll just take the actual gross, actual um yeah, this is it. So I'll take the actual gross and um yeah, I need to clean this by the way. So this is easy to clean to numeric by converting it to numeric. So data frame pandas allows you to do that um, as type float. Now, yeah, so we need to clean it up first by removing the dollar symbol and the commas before we can post the type. So one way to do this would be to use can use a lambda. Let's see if I can remember this. Um, yeah, so they use a map. So map is going to run this lambda function across all of them. So replace this with this. And we can also okay, let's see if the dollar sign will be cool. And let's see if this works. So it's still bother about the dollar sign. So we will also replace the dollar sign with an empty string. Okay, all right. Um, so what's happening here is that we have some additional um numbers that I didn't see here before. Maybe 2291. 22. Okay, let me do some brute forcing. Okay, so I was trying to brute force with regular expressions, but it looks like this doesn't work. So let me just force it for now so that we move on. Um, Oh, so okay. Right. So we have a whole bunch of other things that are not just we have all of these letters of the alphabet. So let's see. Let me just brute force it and remove all of them. All right. So expected two-dimensional container, but got a series. Okay. Okay. All right. So yeah, so I finally got it through. So basically this is variance threshold. Um it's run it and it's given me only the features, that meets that variance threshold, and it gives me the selected values. So unfortunately, I don't have a lot of time to go into detail on all of these methods, right? But what this did was to remove all the low variance features. I really didn't do this properly because I was just taking a single column and try to run variance threshold on it, which is wrong. You really should do an entire data frame. So it means I needed to clean this entire data set and convert all of them to features, and then I could run variance threshold on it. So that is likely going to be the next, task for us to do. All right. So um, there's a lot that you can do with feature engineering, and um, we have other things. We have wrapper methods, we have filter methods, we have recursive feature elimination. So if you want to do recursive feature elimination, again, this is what you can do. Okay. So this is what you can do with this, right? You basically we are using a logistic regression, and then we're using recursive feature elimination to run a series of logistic regression um, training epochs, right? And then each time we do that, we check which features we should eliminate, right? And eventually, this is another interesting way of choosing which ones, the ones that will be left behind. You consider those as, those are the best features that you would go with. So those are all of it. I want to end by just talking about pipelines. So a pipeline is a very powerful tool that we can use with, you know, when you are training. So for example, this is example of how you use a pipeline. If you look at this, pipeline comes from sklearn as well. So you can see that um, a pipeline allows us to throw in a bit of feature engineering before we do our model training. So if you look at this, right, we have a random forest classifier, which we talked about that last week when we were doing random forest. And in this random forest classifier, um, we need to do a bit of feature engineering before we throw the data into our random forest classifier. So sklearn gives us a pipeline. So we create a pipeline, right? And in that pipeline, we it's basically a list of all the things that should be stacked in that pipeline. So the first thing we want is we want a scalar, a standard scalar. So a standard scalar is the standardization we're talking about, the mean and standard deviation, which we just discussed. You can see it right there, Z equals X minus U. X is each X. This is mu, right, which is a mean, and S is the standard deviation, right? So this is like the standardization we just did. So a standard scalar does that for you automatically, right? And then when you stack it in a pipeline, before your random forest classifier, you effectively have created a full pipeline. So for some people, if you look at what we just did here, right? If you look at this, remember I said I did normalization. And in my normalization, I did this normalization part, right? And then I trained, okay? The interesting thing is I could do this with a pipeline in NumPy, right? This same thing is what we are doing here, two steps. So let me just kind of modify this and show you how we can do it. First of all, I'm going to pull this data, same data, I'm going to pull this data set. Okay. So my data will change again, but no problem. I pull this data set in, right? Then I I do this with sklearn. So the first thing I do is I import a pipeline. I import a standard scalar. And what we did here was I didn't use a random forest, so I'm not going to use a random forest. We did just a standard linear regression, right? With multiple variables. Linear regression with multiple variables. Now, so I'm going to take from sklearn dot what's the subset now? Linear model. So I'm going to import a linear regression. So I basically just bring my linear regression inside the pipeline, right? Okay. Then, of course, I have to get the interesting thing is I could actually do the X train and Y train, but let me skip that for now, right? I can now say X train and Y train equals the X train is what we picked from the data frame, right? So we are picking data frame dot um um we're just taking the first we are taking x1, x2, x3, if I can remember. Age and experience. We are taking age and experience, right? We're taking age and experience. Age and experience. That's your X values, right? And then for Y, we are taking the income. Well, not the salary, but the income, right? That's X train, Y train. Um, you know, Y train. And let me display this so we can see X train and Y train. And then we just run a pipe fit, right? We just run pipe fit. So pipe fit is going to basically run that. And we can now say pipe. We want to get, if we want to, um, So let's see how well our model does because like we already have um let me just bring this code here to plot the actual prediction versus the data. So so of course the Y train, Y train, that's just the line, right? And then we now plot Y train versus Y pred, which comes from the pipe dot um predict. And then we can pass, X train again to give us what we are trying to predict. Okay. So we have our pipe, it's done, right? And we can now plot these graphs. And you can see perfect fit, right? In one go, it has basically I didn't need to do a subplot here, so maybe I don't need to do a subplot. But you can see this basically matches this, right? It has fit it perfectly. And I didn't need to do all of this. Essentially, the most important thing I want you to see is that I simply just use the pipeline and I added a standard scalar and then I added linear regression model. And then I took my data X and Y from age and experience and I trained it. And that's it. So, I think that will bring us to the end of today's hands-on. It was really just for us to see what we can do. There's a lot to cover, so I didn't dig in so much, but I want to encourage everyone, take the opportunity and run some of these things. I'm actually going to share some of the code and annotate it so you can go and try it out for yourselves. And for the next task, I'm actually going to ask everyone to use this data set that we have here and do some feature engineering in it. So stay tuned. That's all from me. Thank you very much.